Hello there. In this lesson, we're going to be looking at Avogadros Law. Yes, the same Avogadro that the number is named after also has a couple laws. He did a lot of studies using gases and the relationship between the amount of gas or moles of a gas and the volume, as well as the relationship that involves pressure. So you can see when blowing a balloon here, the boy here is adding in moles of gas into this balloon, and clearly the volume has increased as those moles were added in there. So it's relationships like that that Avogadro did a lot of his studies on. So we're going to look at that and how it relates to the other gas laws that we have already studied. So there's really two situations that we're going to be looking at today. One is if you have a flexible container like the balloon here, where it's obvious that the added moles or removed moles, depending on whether you're blowing in or letting the air come out, will affect the volume, right? The flexible container will change until the pressure outside here is the same as the pressure inside, and then it stops expanding or contracting. So that's one set of experiments looking at the volume relationship. The other is if you have a fixed volume like this metal canister here. It doesn't expand and contract, and so if you pull the trigger here and out comes some gas, that means the amount of gas left inside decreases. And so that's going to affect the pressure and not the volume if the container it has a fixed volume. So this Hoffman apparatus uses a system where the volume can change. So what happens is you got two electrical leads coming from this power supply, one, two, and inside this apparatus there's two electrodes. You can see them going down here and back up, one there and one that's covered in bubbles. So at one of these electrodes, hydrogen will accumulate, and at the other one, oxygen will accumulate as the water decomposes. And what you can see is the volume of the hydrogen is double the volume of the oxygen. And that is because the moles of gas are proportional to the volume. What happens is as the gas bubbles up there, it's going to push the water down and out the bottom of the test tube. And so the volume that you collect will be proportional to the moles that are created. And so since this is a 2-to-1 ratio in this reaction, you're going to get 2 moles of hydrogen for every 1 mole of oxygen, therefore double the volume. So mathematically, Avogadro represented this as a law, and you can see that the volume is proportional to the moles. As one changes, so does the other. So if we got 2 moles of gas and it occupies 24 liters, what would 1 mole of gas occupy? Well, it'd be half of that because it's half the mole, so it'd be 12 liters. And then if we have 30 liters, how many moles would that be? Well, you can use this relationship. It's pretty intuitive, but if you want to work it out using the relationship, or if you have something that isn't as obvious, you can say N2 equals V2 times N1 divided by V1. And so that would be our V2 here is the 30 liters. Our N1 is the 2 moles, and our V1 was 24 liters. And so if you put that into your calculator, out of the calculator you end up with 2.5 moles, right? The liters cancel out, you end up with your moles. So you can use that relationship if you like to go from one volume to another when the moles are changing. Okie dokie, let's try one that's a little trickier. This time we have a 5-liter balloon, and inside we've got 5 grams of nitrogen and 1.4 grams of oxygen. So first off, we know the initial volume is 5 liters. Awesome. The total moles we don't know, so let's work that out first. We'll start with the nitrogen, and we've got 5.0 grams, and we know that nitrogen is 28 grams per mole. And so that comes out to 5 divided by 28 is 0.1786. Keep a bunch of digits for now. Moles of nitrogen. And then the oxygen is the 1.4 grams, and it is 32 grams per mole. And that comes out to 1.4 divided by 32 is 0.043 0.75, so I guess 8 moles of the oxygen. The total moles would be these two together. So we'll add them up, plus 0.1786, and we get 0.2223 moles. Great. So then working out the volume of each of these separately is just a plug and play here. So we want to know the volume of the nitrogen. And we know that the initial volume was 5 liters. We know the initial moles was 0.223 moles. And we know that the final moles is 0.1786 moles. So this one was the total, and this is the part that is nitrogen. And what does that come out to? Well, 5 times 0.1786 divided by 0.2223. And that would give us 4, well, look at that, 4.0 liters of the nitrogen. Now you do the same with the other one, or you can just subtract, right? 5 minus 4 equals 1.0 liter of oxygen. But you can see that we are comparing the total number of moles to the moles that are just the nitrogen. And since moles are all have an equivalent effect on the volume, you can use Avogadros relationship. Now if you have volume and moles like we had in the previous problem there, and you divide, you obviously get the molar volume, right? And so there's some molar volumes you already know, standard ones for standard temperature and pressure, SATP. You know the number of liters for 1 mole. And you can use that along with the molar mass to work out density for a gas. So it's pretty straightforward if you look at the units. So density is always mass divided by volume. The molar mass is grams divided by moles, so there's your mass part, right? And then the molar volume is going to be in units of volume over moles. So all you need to do is multiply to get those moles to cancel out, and you will have the density. So density equals, we'll use the 44 grams per mole, which is the molar mass of carbon dioxide. And then we want to have the volume on the bottom here. So we'll put the 22.4 liters for every 1 mole on the top. And you see the moles cancel each other out. And you end up with, if you divide, ends up being 1.96 grams per liter. So that nice relationship, the molar volume, can help you get the density as well. You just need to use your molar mass. So the other half of Avogadros law is if you have a fixed volume container, so not in a balloon, you need something like a scuba tank or a fire extinguisher or something that has compressed gas in there. And then because the walls or the volume is fixed, the pressure is what's going to change if you change the number of gas particles, the number of moles that are in there. So in our little diagram here, we've got 6 representative gas particles and a certain pressure that we can see on here. And you see the new pressure here has gone up. So that must mean we added double the amount of gas particles in order to end up with that doubling the pressure. So the proportionality is that the moles will be proportional to the pressure as long as the volume stays fixed. Alrighty, so let's use this relationship. This time we got a scuba tank, nice fixed volume container, and its volume is 12 liters. That's not going to change, but what will change is the pressure depending on which gases are in that tank. So what we have is a total of 20,000 kilopascals. That's a lot of pressure. And the tank has 95 moles of gas. 21% of those are oxygen, and so we want to know what the pressure of just the oxygen part is in the tank. So what we can do is, we know the total pressure and we know the total moles. So our initial pressure is this guy, or our starting pressure, and our number of moles is this one here. It goes here. We're looking for the pressure of the oxygen, this one. And we want to know, the last piece of the puzzle there is the number of moles of the oxygen. We know that air is 21% oxygen or thereabouts. So let's take 21% of these moles. So 95.0 moles times 21 over 100. So 21 is the oxygen, 100 is the mix. And what do we end up with here? So 95 times 21 divided by 100. And I get 19.95. 19.95 moles of oxygen. So now we can use this relationship and solve for P2. So P2 equals P1 N1 times N2. So the initial pressure is 20,000 kilopascals. The number of moles that's oxygen is 19.95 moles of oxygen. The total number of moles was 95.0 moles total. And let's see what we end up with here. 20,000 times 19.95 divided by 95 equals 4,200 kilopascals is due to the oxygen. There you go. Nice easy relationship. So our last thing here is to combine Avogadros law with the other three that we learned in the previous lesson. If you remember, Boyle's law is P1 V1 equals P2 V2. And if you remember Charles' law, it was V1 over T1 equals V2 over T2. And Gay-Lussac's law was P1 over T1 equals P2 over T2. And now we're adding in Avogadros law, and it doesn't matter which version you use. We can use the volume one, so V1 over N1 equals V2 over N2. Just to help you find where the N is relative to the others. You see it's on the bottom along with temperature, like in Charles' law, and so you can add it in down here, and you've got what I call the mega combined gas law. Sometimes when they say combined gas law, they don't include the moles. Alrighty, so there you go. It's a handy tool you can practice with, and you won't have to memorize all those other relationships because you have the one that gives you everything. Alrighty, so one last headache here. We're going to see if we can figure out the volume using the mega combined gas law. So we're looking for the new volume given all these changes that occur. So we want V2, and that is going to equal P1 V1 all over N1 T1, and we bring N2 up here and T2 up here and P2 down here. Okay, so let's start filling things in. The initial pressure, blah, 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 starts at 100 kilopascals. So we'll put 100 kilopascals in for the initial pressure. The initial volume, 5 liters. Great, 5.0 liters. We keep going on the top here. The new number of moles. We added 0.1 moles to 0.2, so that means new number of moles is 0.3 moles of gas. The new temperature, 10 degrees Celsius. We know it needs to be in Kelvin, so that is going to be 283 Kelvin. The initial number of moles was the 0.2 moles of the carbon dioxide. The initial temperature was 30 Celsius, which is 303 Kelvin. And our final pressure was 90 kilopascals, so pressure went down a bit. Great, so we can have a look here, make sure everything cancels out. Kilopascals cancel out, great. Moles cancel out, great. Kelvin temperature cancels out, great. We should end up with liters. Alrighty, let's see what we get. Drum roll, please. Tickety tick. And I end up with 7.8 liters of carbon dioxide in the balloon. All right, there you go. That's about as painful as it gets. We'll talk to you soon.